We've got two, I'm sure they're going to be very interesting, but incredibly knowledgeable people talking about this. We've got Professor Devin Sapsford, and then we've got Jeremy Reece as well. Other way around, sorry. They're going to introduce themselves, so I'll take a seat. And yes, thank you.
Good afternoon, and thank you very much for the introduction. This afternoon we're going to be talking about our innovative approach for removing heavy metals from former mine water. Might sound like a bit of a dry subject, sorry about the pun there, but it's a piece of research that's been going on here on the island over the last year or two. So, quick introduction. Just so you know which way round we are. I'm Jeremy and this is Devin. I work for the Isle of Man Government as a project manager and have been looking after the programme of work to do with Peel Marina and dealing with the sediments and the challenges of Peel Marina. And my colleague, Professor Devin Sapsford, is from Cardiff University, is also a UNESCO chair in the development of a sustainable geo-environment. And I'll leave you to talk to Devin about what that is. But this is who we are. So, why is mine water a problem here on the island? You may say there's no mining industry at the moment. We've never, there's not a problem. However, if you go back in history, go back to 1300s, the very first signs of mining were seen here on the island, particularly mining copper, iron and lead. And then if you go forward to about 1800, that's the start of the main mining boom here on the island. The first mine was at Bradder Head, where you could see the seam of the metals in the rock on the headland, and they started digging that and carried on mining. So Bradder Head was one of the early mines, and then mining then spread across most of the island. When we talk about mining, sometimes the scale of what we're talking about can range from everything from a small little hole. Somebody's seen something on the side of a riverbank and they think, is that a seam of metals? And they start digging and it stops, and you've got a hole about 1 metre long. Sometimes you've got tunnels going into the hillside where they've got a bit, all the way through to the big mining networks with the shafts and the tunnels that we see around Laxey and Foxton. So, where did the mining take place on the island? I hope you can see the diagram. These are all the shafts, all the mine shafts across the island. So you can see, starting from sort of Mackle at the top, all the way down to pretty much down to the Sound. You've got mining going on across the island from about the 1800s. It's quite easy to spot Foxton. That's Foxton. Surprise, surprise, that's where all the mining was. You can see the concentration of lots of Laxey, and the mines are going up towards Stathar. And it's all to do with the geology. Where the geology in the ground has produced the metals, that's where the mines were. So, in terms of the island's mining history, we were actually a very significant mining nation back in the 1800s. At one point, the Isle of Man produced 20% of the zinc that was produced right the way across the island, in zinc per year, that was produced across the whole of the British Isles, and 5% of the lead. In 1854 to 1855, slightly before I was born, the Laxey mines produced more zinc than the total of the rest of the Isle of Man. The Laxey mine produced more zinc than the rest of the mines across the whole of the UK put together. The boom didn't last that long, but boy did we have a boom at that point. So instead of .com, we had .zinc. And when you mine the ore, it comes out as rock. Sort of the metal is formed into the rock. So when it comes out, it has to be crushed to actually get the big blocks of metal and the big lumps of metal out. What then happens is it's heated up and melted, the rest of the rock sort of goes away, and then you've got the pure metal. But because here on the island we didn't have a plentiful supply of fuel, the mining and the crushing of the rock to get those big lumps out, that's all happened on the island, but the actual smelting process, the heating process, was usually done across. So that's why there aren't blast furnaces here on the island and things like that. So everything carried on till about the 1930s, when the last mines here on the island closed. So we're now 100 years after the last mine closed on the island. So why is it a problem to us? Well, mining usually involves digging holes. And anybody who digs a hole knows that a hole fills with water. And if you've got a hole full of water, you need to drain the water out of it. And that's where the problem comes. So, when the mine's closed, usually the miners, the mining company would decide the mine's not being productive anymore. They would cap over the mine shaft just to make sure nobody falls down the mine, sell off any equipment for scrap or for reuse sometimes to another mine, and then walk away. So any water that came out of the mine, any areas where a lot of the metal had been processed and crushed above ground, they just walked away from it. Now, these days, our planning system and our environmental regulation system means you can't do that. But 100 years ago plus, you could just walk away. And that's left us here on the island with a legacy of mining problems where we're getting metal getting into our, particularly into our rivers and our streams, in the areas where the mining used to take place. When you look at streams that have got metals in it, usually you don't see anything. The only time that you generally see problems, or you normally see it, is where there's iron. Now, for those of you who know Foxdale and the big mining network that was underneath Foxdale, the water that comes out of the mine comes out of a horizontal tunnel, an adit as it's known, and this is where the adit comes out into the stream. Now, this to the locals is known as the tomato soup factory for very obvious reasons. But you've got the iron ochre very visible there in the riverbank, and even the stream of the river. If you walk down, it suddenly changes. The stream and the rocks are stained orange because this has been coming out for 150 plus years. But the moment you walk past there, the stream is clean. So it's very easy to actually see a visible staining on the riverbed. But where you have other adits elsewhere that are emitting lead and zinc, you can't see anything. It looks like pretty clean water. And the metals get into the water in two ways. One of which is they will just be carried as little particles, little like mud. You get mud in the water. You'll get mud and metal particles washing off the surface into the streams. But also, because of the contact between the water and the ground, you can actually get the metals dissolving into the water. And it tends to come from two sources. With the old mines, it can come from washing off the surface, but it can also come from the actual mine water, the groundwater that's gone through the mine. So we have two sources and two types of water, particularly two types of metal, should I say, the particles in the water and the dissolved metals. So going back to our question here on the island, why is that a problem? I'm going to take you across to the west of the island to Peel. Peel Marina, as many of you know, is an impounded marina, so the river there runs in, flows in, and as the water comes in and it hits the big stilling pond, the sediment that's carried by the river drops out. The river there deposits about 3,000 tonnes of sediment every year, because it's coming down from the catchment. All rivers carry sediment from the river banks, from the ground around it. Normally it just continues out to sea. But because of the settlement pond that is Peel Marina, it settles out for us. And that sediment contains lead and zinc and other metals, but it's predominantly lead and zinc that comes from the mines in the Foxdale area. And that level of zinc, because of the modern environmental protection rules that look after the aquatic life out in the sea, means that those levels are just a little bit too high to allow it to go out and be deposited at sea. So DEFA and DOI, two government departments here on the island, have been working together on a number of projects looking at reducing the amount of metal coming down into Peel Marina. But what we're trying to do is, instead of saying, well, we'll just keep handling it, what we're trying to do is to go back to the sources and actually work at the source to try and solve some of the problems. So, as a little explainer, so anybody whose sense of geography is challenged by this, I do apologise, the north is actually that way, but I couldn't turn the screen around. So if we go up to Foxdale, we've got Crossvein Mine and Dixon's Mine. Crossvein Mine's also known as Stuff the Wind Mine for some of the locals. We've got a big barren area that we'll see in a minute, where we've got lead coming into the watercourses. Dixon's Mine, again, we've got lead coming into the watercourses. Then as you go down into Foxdale itself, at the top of Foxdale we've got Keonslew Reservoir. We've got an area of uncapped mine spoil. We've got the main added out of the main Foxdale mine, adding zinc and lead into the watercourse. The streams then come down through the valley, and all the time it's mixing with sediment that's coming off the riverbanks, it's coming up, washing off the fields and the land around, as is a natural process. And it comes down to Peel Marina, which is where some of the sediment with the zinc and the lead in it settle out. So, before I talk about this, it's what's the scale of the problem? If you take Crossvein Mine, Dixon's Mine and Keonslew Reservoir, between the three of them, they release just over 450 kilograms a year of lead into the river and just over 400 kilograms of zinc into the river. That's quite a sizable thing. I've often wanted to kind of just bring in 400 kilograms of lead and plonk it on the desk, but I appreciate I can't pick up that sort of weight. So, but it's quite a big amount of metal going into the environment every year. So that's the level before anybody started doing any work. So looking at what's our plan? Well, short term, the first thing that we did was to dredge the sediment out of Peel Marina. If you cast your mind back to COVID, 2020, 2021, those sorts of times we were in Peel Marina digging some of the sediment out and taking it out, not putting it out to sea, but bringing it to land. Other short-term plans then are to remediate Crossvein Mine and actually deal with one of the main sources of lead. If you can turn the tap off at the top, give it a bit of time, it will clean through the environment. Likewise for Keonslew Reservoir, putting a settlement pond below the reservoir to actually allow some of those particles to settle out. Simple things that should hopefully allow us to reduce the amount of metal coming down. So, as I say, there's Peel Marina. The excavators on the floating barges, dredging the silt and the sediment out, and then that was moved up to a lagoon, you can see the bottom left-hand side, where it's been allowed to dewater, take the water out, let it dry out, let it get a bit more solid, and then, so over the two spring times, we removed about 23,000 cubic metres of sediment. It's a big amount of material that we took out. Moving on to Crossvein Mine, for those of you who aren't familiar with the site, you can see from the aerial shot here, there's one shaft here just in front of the mine building in the chimney, there's another shaft here in the fenced-off compound, and the mining tunnels run between the two shafts and extend out either side. So that was the main mining area. Because they're following a sort of quite a narrow seam in the ground, each of the tunnels are one on top of each other, but they're all in that line underground. But as you look beyond, particularly that line, you see this big dead area, as it's known. After 100 plus years, nothing's growing on it. That's a fairly sure sign that there's heavy metals in the ground. And that's the area where they used to process and crush the metals. As I mentioned before at the beginning, where you were able to just walk away when you finished a mine. It's essentially as it was left when the mine closed. So we talk about mine remediation. What on earth is heavy metal mine remediation? It's often done in a number of stages depending on what each individual mine needs. So first thing was to stop the unauthorised vehicles disturbing the ground. So we had vehicles driving around on the dead area, and that was churning up the ground. And if you've been on the beach and you look at the sand, as the water comes in, if the sand's loose, it just washes around. And that's exactly what's happening here. The fine material, which has got the little bits of metal, the little particles of metal in it, washing into the streams, washing down the valley and ending up in the River Neb, ending up in Peel Marina. So by stopping it actually churning up to start with, has brought a benefit. The other thing is that you've got Southborough Rule in the bottom left-hand corner. So water coming down the side of the road, by doing some drainage ditch maintenance, we're keeping the water away from the site. So rather than bringing extra clean water onto the site and getting it contaminated, we're actually just keeping the water going around the site. Next stage then was to install leaky dams. Now I'm a civil engineer, and leaky dams to me is a complete kind of contradiction in terms, because the dam usually is supposed to keep the water back. But the concept of the leaky dams is quite interesting, very, very simple. On the left-hand side here, you've got the water washing off the site, and you can see the sort of muddy water. That's got all the fine bits in it, which are all the fine particles with the metals in it. So you can see how easily it moves when it rains. So one of the types of leaky dams that were put in was basically a heather bale, just put into the stream. What that does is it slows, as the water comes down the stream carrying the fine bit in it, it just slows the water down. If you slow the water down, you make a little settlement pond. And that little settlement pond, it's not 100% waterproof because it's a leaky dam. You've got a heather bale, but it's enough just to let the material, those little particles, just settle out and collect at the bottom. This is the same place 18 months later, and you can see all the way back there, all of that material, and again, it's all the really fine stuff, which has got the high metal content in it. It's very effective. We've tried some with a lot of timber slats with a little gap in between as well. It has two benefits, one of which is it collects all the sediment with the metals in it. The other thing is that when you get heavy rain, it's holding some of that water back, so it's what's known as natural flood management techniques. And by holding the water back in the uplands, it stops that whoosh of water coming down the valley. So there's two benefits to it. So we've put about 50 of these, mainly the timber dams, down below crossvein to catch the sediment. And what you find is the first one at the top of the run ends up like that after about 12 months, 18 months. The second one, the third one have got a little bit of sediment. Once the first one fills up, the next one starts. It grows, but with sort of 10 of them, by the time you get to the bottom, it's actually the vast majority of the sediment's already been taken out. So you're just holding it on site. Going on then so that's work that's already happened up at crossvein. Going on to the next stage then is to actually cap the majority of the dense area. By creating a cap over the top, you're stopping the rainwater being able to actually wash that material away. What we're looking to do with this one is to use treated material, to actually use the material that's been dredged from Peel Marina, treat it so that it's safe to use in that environment. It's already pretty safe. It's not what a lot of people think of it as. But to treat it so that it's safe, it complies with all the environmental rules, but to form the cap, but actually use some of that problem material to solve the problem. And it also saves in quarrying 16,000 cubic metres of material, which again has a big carbon footprint. So if the planning application is in the system at the moment, if that's allowed to go ahead, then capping the sites would be the fourth step. And then the last step, Dixon's mine, which I mentioned earlier in the diagram, you've got the old crushing floor here, the washing floor, and you've got a big pile of spoil with a stream running along the end of it. And what basically happens when the stream's running fast, it erodes to the bottom of the stockpile, and bits of the stockpile drop down into the stream, which again is not a great idea. So we're looking to do something there to either move that away slightly or to keep it safe. And then the last bit of things that we're doing at the moment, Keelsley Reservoir, again, Foxdale, we've got the main road through Foxdale, past Betridge's, up the hill to the MSPCA at the top. Keelsley Reservoir is tucked away at the top of the valley. Most people, if you've walked along the footpath, you'll know it's there, but most people probably don't even notice it's there. But again, that's because in the 1950s, when all of the mining work had stopped, we think that a lot of the material was reprocessed to try and have another go at getting the metals out of it, and what was left, the really fine stuff, we think was actually put into the corner of the reservoir, so that the bed of the reservoir now has got a lot of heavy metals in it. It's not used as water, it's not used for drinking water, so there's not a health issue. But again, you want to try and turn off the taps at the top of the valley. And again, because some of this is particles in the water, a settlement pond just downstream from it will allow that to be settled out. And then, what else are we doing? Looking at other sources. Obviously, there's a lot of mining across the whole of the Neb catchment. Now, what I've been talking about is we've got plans of what to do with trying to get the particles out of the water. That's the easy bit. The hard bit is how to get the dissolved metals out of the water. And because that's the hard and complicated bit, this is the point I'm going to hand over to Professor Devin Sapsford, who's going to take you through the next one.
Thanks, Jeremy. Okay, I want to start just by taking a step back, actually. We talked about the Isle of Man there, but globally, this is an absolutely enormous challenge. So if we look in the UK, here's which one's the pointer? Is it that one?
No, it doesn't work on the screen.
Oh yeah, old-fashioned analog. So this is an example from Cymyswith in mid Wales near Aberystwyth. We're talking about a total number of abandoned mines or legacy mines. No one's obviously got a record of it globally, but it could be into the millions. Certainly hundreds of thousands. Certainly just tens of thousands in the US, for example. So in England and Wales alone, we're looking at over 2,100 kilometres of rivers fail to achieve the European Framework Directive. And even when excluding coal mine drainage, I'll talk about why you get this problem from coal mine drainage as well. So just looking at old metal mines, 226 water bodies are impacted, with a further 226 probably impacted. So that's in England and Wales. This is a big problem. So you think pretty much wherever there's been mining for metals in the world, there's a high likelihood that you'll have a problem with the mines impacting water quality. Even coal mines, so people are, what's the problem with coal? Yes, you can have fine coal that can be a particulate problem, but actually coal has cannot have a lot of pyrite in, fool's gold, which is one of the main kind of minerals that's responsible for causing this drainage. But then we have lots of metal mines in England and Wales, and the mining legacy goes back. There's plenty of evidence of Bronze Age, goes all the way back. A nice little anecdote for you. One of the worst mine drainage in the UK is from Paris Mountain on Anglesey, which is a UNESCO geopark. But the mine water there goes out to sea, and Paris Mountain was the world's biggest copper mine in the sort of 18th century, and they used to bring in the wooden ships into the port deliberately because the mine water would kill all the shipworm on the bottom. It would solve their problems for them, and that mine water is still discharging to this day. So this is so that's just the UK. Globally, huge, and I'm just talking. This is just legacy mines. Of course, now you're looking at huge amounts of mining. The amount of mining projected to 2050 to meet the global metals demand is absolutely huge, and we're talking orders of magnitude larger mining than here. So the water quality challenges are, enormous. So just here's a couple of examples. You kind of characteristic. This analog. It's just from South Korea. This is from South Wales. Coal. This is from the coal fields. This is over in West Virginia. Again, that's actually from coal mines. But you see this characteristic orange colour, like Jeremy was saying. It's not always there, but whenever you're seeing this, it's iron, and it's iron 3 hydroxide. There's a bunch of iron minerals that that you typically find. Essentially, when I'm first introducing students to this, think of it as rust. It's pretty similar to rust. And that's coming from the iron, and that iron is coming from the breakdown of the mineral pyrite, fool's gold, which as it breaks down, releases the iron and sulfuric acid, which tends to mobilise other things. But you also get mine drainages that don't have the iron, and are not as acidic, but they come from lead and zinc minerals that can also break down. Essentially, you can think of them corroding, and they can release things into the water. So running off from these sites, you can get lost in just the interesting mineralogy. So the white here as well as the orange, that's aluminium minerals coming out with the iron. from this particular coal mine drainage, you get some aluminium. Big scale, large scale problems in some places. And I'll just point out that just as the Isle of Man is a biosphere reserve, you think about all the other ones globally in the geoparks, I'm sure, and many have the label of geopark or biosphere reserve, there's some link to mining heritage in a lot of them, so I'm pretty convinced you'll find this problem everywhere. So my work is mine waste and mine water management, and particularly on the treatment of the dissolved, the difficult to remove dissolved stuff. So how do you do it? If you've got the money, you can build hard infrastructure, so-called active treatment. I'll come on to that, but that's the defining thing there is that you are having to put in energy, reagents, you're stirring, pumping. It's much more of a standard chemical treatment process. That's great if you can do it, but as Jeremy said, one of the big problems with the legacy stuff is that the mine owners walked away with no legislation in place to pursue them. And in fact, in England and Wales, it was only changed in 1999. That it was later than that actually someone closed that legal loophole. So before that, mine owners just walked away. So there's no money to treat. So as a result of that, the legacy mine water, people have been looking at passive, if you like, nature-based treatment systems, soft infrastructure with no energy or limited reagent addition. And that's been really started coming out of the States in probably the 1980s, and has been developing slowly since then. The first treatment system that I'm aware of in the UK probably was treating coal mine drainage in about early 90s, although there is a site in Wales that has a claim for 1960s. So here's what active treatment looks like. This is the Wheel Jane treatment, mine water treatment plant in Cornwall. Treating up to 500 litres per second of contaminated water at pH 2 point something. Lime dosing, so these big silos of lime. You precipitate. So what's happening there is you're using the lime to manipulate the chemistry of the water to pull the pH up high, at which point those metals don't want to be dissolved anymore and they precipitate as a solid, and you get this kind of soupy colour, and that's actually the solids precipitated, and then you can filter those out. There's another example just from West Virginia, exactly the same treatment process. You see towers of lime there being fed into the water. So, big problem started in England and Wales and Scotland as well, with when the coal mines closed. So all of the coal mines closed. To keep the mines open, when they were running, of course, you have to dewater the groundwater continuously to keep the mine dry. But the mine's closed, the groundwater returns, and then any of these products that formed can start to leach out into the environment. So the big problem in the UK from coal mines was just iron, as I said, from the pyrite content. And it's relatively easy to treat. It's still not a double, but it's comparatively easy to treat. And you see there's about 80 of these kind of schemes now in England and Wales, and some in Scotland, where they use the iron wants to come out of the water if you just give it a little bit of oxygen. So contact with air, then you see the iron oxidizes, forms this kind of rust-type compound in these settling ponds, starts to settle, and then they just filter through these constructed reed beds. Here's another example looking down, different site at the end of the M4 near Swansea. So you have settling ponds, the iron is being oxidized, forming this solid precipitate, settling in the ponds, and then you can see that they go through these constructed reed beds to filter out the iron. Great. Downside is they're large, but what about the stuff that's dissolved, which, as Jeremy was saying, stuff that doesn't easily want to come out of a solution and stay dissolved? And that's where you come, especially with zinc, metals like that. They don't really want to come out of solution as easily as iron. They won't respond to being aerated and form a precipitate. So people have been looking at, okay, we know how to treat passively nature-based solutions for, if it's just iron, and as I said, 70 to 80 of these schemes being built across the UK to treat the old coal mine drainage. But what about those metal mines where you may have a bit of iron, but you have a lot of things like lead and zinc? So people have been researching, including me, at other nature-based treatment systems. So what you're trying to do with these is come up with some way to mess with the geochemical environment to encourage those metals to no longer stay dissolved but be removed. So one of the common approaches is to use sort of a biofiltration system with composted materials, and that you can get a bunch of reactions that happen here facilitated by naturally occurring microbes that can remove zinc, but we're still at a really early stage on understanding how these systems are built and operated. They probably have the most experience of this in the United States, but they weren't really built for zinc removal, and this is the focus of where we're at today. So there's ongoing research in the UK and across the world on problem metals that want to stay dissolved like zinc. So this is one approach. So another approach, this is where some of my research came in. We have, I work with the Mining Remediation Authority in the UK who are responsible for the legacy mine water. And we had a trial here down in Cornwall, and we were using a sort of simple filtration system to remove the iron, because that was particulate, you can just filter it out. But the zinc in the water was still a problem. And we ran it through a little bed of limestone. And based on some earlier research, the reason I did this is because I had a hunch that the water's also got dissolved manganese in, and I had a hunch based on previous research and other things that we've done that might remove the zinc as well. So we had this limestone material, and you can see there's the limestone, this little filter at the beginning, and then after about 3 months, I'm not sure you can see it here, you can see the limestone has gone black and it's working its way down. And that coating is classic colour. So like iron is always orange. If you see orange sediment, it's usually iron. If you see black sediment, it's often manganese oxides. And sure enough, it was coated up with manganese oxide. So we convinced the manganese to be not dissolved in the mine water and come out as manganese oxides on the limestone. And what we found in Cornwall was that co-removed the zinc. So we had a bit of a story where if you have manganese in the water and zinc together, you can perhaps co-remove them. So I was presenting similar work at a mine exchange conference in Wales a few years back when Jeremy came up to me and introduced himself and explained about some of the background that you saw earlier on and invited me over. So I came over and we were just exploring some of these sites, and we went on to the Keon Slough Reservoir. And Jeremy, you just happened to pull up on your laptop, oh, I've got some data from here, and I looked at it and I saw, oh yeah, you've got dissolved zinc. And then I said, oh, have you got any dissolved manganese? And, oh, you've got dissolved manganese. So I was like, oh, okay, that's interesting. And then I explained the work we've done in Cornwall, so showing that if you've got dissolved manganese, you remove that, you can remove the zinc. So the first, and then the discussion went on a bit further about sources of limestone, and then I think the discussion moved on, well, we also have these shells on the Isle of Man. So, oh, that's interesting, they've got similar mineralogy. So we did an initial trial where I was back in Cardiff now. Jeremy sort of put these shells in a string bag and simply left them in the Keon Slough in the stream. Left them there for a few months, I think. And then you packaged them up and sent them over to me. We used a technique called X-ray fluorescence, where you shine a sort of X-ray beam to do some analysis. And sure enough, on the surface of the shells, it was picking up manganese and zinc. I thought, oh, reported that back to Jeremy. That's interesting. And then from there, we were lucky to get an MSc project student from one of our courses in Cardiff University, Yagiz Kaya, who wanted a project on related to mining remediation, because he now works in the Turkish government on that topic. So he came over and put together the trial system with Jeremy and James, and you had a tank of limestone, and we wanted to compare it to a tank of these scallop shells. So the header tank there, just the mine water coming in from the stream, containing dissolved zinc and manganese. And we operated, Jeremy and James operated this for over a year. And this is what we saw. So this is the removal of dissolved manganese. So the stones are one of the reactors with limestone fragments in, and the other one is the shells. And this is percentage reduction in dissolved manganese. And this is days of operation for just over a year. And you can see that pretty quickly, firstly the stones, they were up to almost 100% removal, but then the shells over time are actually outperforming the limestone. So dissolved manganese was being consistently removed in those reactors. What about zinc? Really interesting. Removal of dissolved zinc. You've got the limestone, again the blue, that was being removed 50 to 60%. You might think, oh, that's not that good, but even that's good because the actual zinc concentrations are quite low, and the lower the zinc concentrations in the water, the harder it is to pull it down further. So that was pretty good, but then I saw the results from the shells, which were consistently sort of, between 70 to 90% over a full year. Nothing added, no other chemicals, nothing added, just the shells doing their thing. And that's impressive, that's really good. So how were manganese and zinc being removed in the system? So I came over in August and we took some samples. It was filled with excitement, a bit geeky, but I opened the top, I was like, oh! And then I saw this and I was like, oh, wow! You can attest to that. For me, this is very exciting. To you, you're probably like, okay. So what I immediately saw is, black precipitate everywhere. Black precipitate manganese. That ties in with the water quality data that we've seen. And it was kind of settled into pools of here. And then we sort of got into the shells and you saw some of this black precipitate everywhere. Other metals were being removed as well. There's a little bit of iron, a little bit of lead. So really interesting. So where are we now? We're just like going through all of the analysis to kind of figure out what's going on. This is some scanning electron microscopy images of some of that. If I go back, just a little scoop of that black sludge, dry it out and put it under a microscope. So the field, that's 100 microns. So what's that, 1/10 of a millimetre, and this is 100th of a millimetre. And you can see one of those sort of little grains of precipitate. Here it's interesting, you see some freshwater diatoms got caught up in there. There's these little silicon skeletons from the stream water, but you kind of made this little cemented lump of precipitate. And this is just some closer up images. There's some bits of biological material that have been washed in this system. And I should say that we're also doing a full microbiology, microbial community analysis with a colleague from biosciences, because it is known that manganese oxide, there are a type of bacteria that make their living, power their respiration from oxidizing manganese from its dissolved form to its solid form. So we're pretty sure that there's some interesting microbiological action in here as well. But what can you see? You see fragments of material washed in, but more importantly, you see this material is being cemented together by this manganese precipitate, and clearly it was co-removing the zinc. There's just a close-up. This is 1 micron, so 1/1000th of a millimetre, so you can see the scale of precipitate that's building up in the system. So with the same analysis, we're able to not only image, but then use X-rays to kind of get an analysis. And this is an elemental map. So you change the setting on the machine and suddenly it lights up and gives you a composite image, and you can probably see it's quite greeny, and that green is the manganese showing up. So then you can map other elements. So this is that lump of precipitate. and you can see a bit of silica, there's the manganese, all across that precipitate. So the interesting thing was, it's not localised in one spot or anything, it's kind of, I think, cemented up everything, but there's also a bit of aluminium, a bit of iron there, importantly is the zinc associated with that, and lead as well. And you could just kind of pick out the grain, showing that the metals are associated with the precipitate. But what we're finding is, unlike our previous analysis where we could see specific spots where all the metals were being removed, in this system the metals seem to be just coming out on that cement, natural cement that's forming on the surface of those shells.
Devin, I'm really sorry.
Oh, time to go.
So
I've almost finished.
I've been watching the countdown.
Oh, okay, so for next steps, 2 slides I've got. How to upscale. This is the big. Is the problem solved? Absolutely not. We've just done the very first stage, proof of concept. This shows like potential, but we're a long way from going to a full system. But we're on the start, and we now know we have a mechanism that we can utilise. And so you've got to give a lot of thought about how to actually upscale these things and then maintain them and operate them. So in conclusion, serendipitous collaboration with me as the UNESCO chair, with Jeremy. The proof of concept work has been done. We need to now look at scaling up, which is a lot of problems to solve yet. And that given that very many biosphere reserves and geoparks globally almost certainly have this problem, we're hoping that this is a great example of an impactful collaboration. Thanks.
Thank you.